Hello again. We're going to do sections 3, 4, and 5 of hazard communication. In this presentation, as you can see, I'm in my backyard again, and we have a couple of hummingbird feeders out. Boy, we get some big hummingbirds. Look at the size of that hummingbird in Spiro. So if you want to see some really big hummingbirds, come on down to Spiro. In the meantime, we'll get going here with this. And again, we're doing my hazard communication. And why are we doing hazard communication when you've got it in other classes as well? Because it is important and it is misunderstood. And you are going to understand it, I hope. Now we're talking about section 3, review of common health effects. There's a range of health effects caused by chemicals. That makes a little sense, doesn't it? If a chemical replaces so much air that there isn't enough oxygen to breathe, it can cause simple asphyxiation. And they do not honor if alarm to sounding nitrogen. And you can see that confined space there from one of the videos we've looked at where two people died, yeah. There are many simple asphyxiants: carbon dioxide, hydrogen, nitrogen, neon, krypton, and it's very bad, especially if you're Superman, acetylene, helium, nitrous oxide, argon, ethane, methane, propane. They are some simple asphyxiants. Chemical asphyxiants reduce the blood's ability to carry oxygen, which can lead to suffocation. Examples: hydrogen sulfide, carbon monoxide, and hydrogen cyanide. Those are two very common origins of carbon monoxide. That's why you don't start your car in the garage unless you open your garage door first, because the carbon monoxide can build up in an enclosed garage pretty quickly. Sensitizers and allergens set up a reaction in the body so that even minor exposures can cause a reaction. Corrosives can severely damage the body. Acids and bases are corrosive chemicals. We know what acids and bases are. They're at the extreme ends of the pH range. Damaging to the skin, eyes, and lungs. The extent of damage depends on how long the corrosive is on the skin and the strength of the corrosive. There's a warning sign: danger, corrosive, avoid contact with eyes and skin. The muriatic acid is a corrosive. You want to use that with care. Mutagens can cause genetic changes and can lead to birth defects or other problems in following generations. So examples there: ionizing radiation, hydrogen peroxide, and bromine. What are teratogens? Compounds that can harm the developing fetus, causing birth defects or death. I don't know why they show two pictures of kids, but examples on construction jobs, there could be heavy metals, particularly lead and mercury. Cancer-causing chemicals must be listed on a safety data sheet, even if the amount is only 0.1% of the product. So bear that in mind. If it causes cancer, if it's a carcinogen, it has to be listed on the SDS, even if it's only 1/10 of 1% of the product. There are a few known and suspected human carcinogens. Asbestos, that's pretty well known. Benzene, beryllium, cadmium, asphalt fumes, silica. Asbestos is getting more and more out of the common circulation. You mentioned it before, if you have an older building and you have tiles, floor tiles in it, and they're 9 by 9 inches, they probably have asbestos. They're made out of asbestos, and they're going to be torn up. You need to have a special crew do that. I've seen them do that in an older, wasn't that old hotel, and they were in full level A suits, and it was quite an operation. Chemical effects on the body depend on the physical form of the chemical, how chemicals get into the body, route of entry, the dose, the toxicity of the chemical, and the individual's reaction to it too. That can be a factor. The dose makes the poison. Paracelsus in 1493 to 1541, that's even before my time. All substances are poisons. There is none which is not a poison. The right dose differentiates a poison from a remedy. So he's kind of had got that's somewhat true. The dose response curve shows how people respond to toxic chemicals. So there's the dose goes up, the percent response seen in the population goes up. And there's the dose response curve for alcohol consumption. I don't want those look like shot glasses, I guess. So again, 100 at four drinks, 5 drinks. Yeah, it's getting there. How do chemicals enter your body? By breathing, which we call inhalation, absorption through the skin. You get it on your skin and it actually gets absorbed into the skin. And again, if your skin is intact, it's going to help. And if your skin has cuts or openings or even scrapes on it, it's going to absorb a lot easier. Swallowing, ingestion, and usually that's accidental, but sometimes people do it once. Well, if you do it by mistake, that's called suicide. But it splashes into your mouth, something like that. Injection, and that's not through a hypodermic needle, but it could be, but it's usually step on something sharp or get cut with something. So what's the most common route? It's inhalation. Airborne chemicals are breathed in through the mouth or nose, or both. Gases and vapors can reach deep into the lungs, and your lungs have about 90 square yards of surface area, and that's why the exposure is so quick and so great, because there's a lot of area in your lungs. Particle and droplet size affects where the chemical settles in the tract, which influences the diseases. I'm going to do this right here. There you go. Absorption. If chemicals get into your body, they may be able to pass through to your bloodstream. Open wounds can increase absorption. Chemical properties affect absorption. So somebody there's rinsing their hands off with some grease or something, and that shows some dermatitis from kerosene. Are all areas of the skin equally protective? So the skin is what? It's your largest organ in the body is the skin, and it's there to protect your body. So are they equally protective? No, all areas of the skin are not equally protective. Relative to the forearms being 1, so the other one's abdomen's 2.1, upper foot 1.5. They are, it's not the rate of protection, it's the rate of absorption. It's higher in most other places. Ingestion, how are chemicals ingested? Chemicals can be accidentally transferred to food or drink and be swallowed. Airborne dust can get onto the face. So in other words, you could be handling it and get on your sandwich while you're eating it, and ingest the chemical, not even know it. Injection, anything that pierces your skin allows chemicals to enter your bloodstream immediately. Blowing out drill holes with high pressure air, that can do it. High pressure air can do it, so can a sharp object. What's the difference between acute and chronic exposure? Acute, high exposure over a short time period, usually minutes to a few days, or after exposure stops, damage may or may not reverse. It won't get any worse probably, but it's not going to, it could stop. Chronic means low exposure over a long time period, usually years, can cause disease or other irreversible effects. What is a latency period? What's an example? Asbestosis and mesothelioma can take up to 25 years from initial exposure to appear. That's called a latency period. What's the difference between local and systemic harm? Some chemicals harm the body at the site of their exposure, such as an acid burn. Other chemicals can affect entire body systems, such as lead and alcohol. Some can do both, such as alcohol and organic solvent you may use at work. Multiple chemicals may have magnified effects when combined in your body, like alcohol and solvents, asbestos and cigarette smoke, exposures at the World Trade Center cleanup. What a mess that was. Section 4, overview of chemical hazards. All chemicals are found in one of 3 forms, solid, liquid, or gas. Example of categories. Solid, actually dust, fiber, fumes are all solids. They have particles in them. Liquid is aerosol, mist, gels, adhesives, and gas, acetylene, oxygen, carbon monoxide, nitrogen, all gases. And what's the most common thing that we see in all 3 is, of course, water. So liquid is water, the solid is ice, and the gas is steam. Solids released into the air can get into your body and harm you. Yeah, they sure can. Dust from sanding, fumes from welding. Liquids can come into contact with the skin or eyes and harm that area or be absorbed by the body. Guy looks like he's got some white on there from that caulking gun. There's a good old muriatic acid again. Gases and vapors that a worker breathes can reach the lungs and cause harm, even painting. It's important to understand these physical properties of chemicals. pH, well, we kind of talked about that. Vapor pressure, flash point, ingredients for a fire, explosive limits, vapor density. With corrosives, concentration is critical. Acetic acid, 90% solution destroys skin, has a pH of greater than 2. Or excuse me, less than 2. And the 6% is vinegar, and we put it on salads. The pH is about 4.5. Vinegar is an acid. What does vapor pressure of sulfuric acid say about the inhalation hazard from a spill? Sulfuric acid vapor pressure is 0.001 milligrams. What is the chemical's flash point? The temperature at which a liquid gives off enough vapor to flash if there is a source of ignition. In other words, it won't burn, but it'll just flash. That's the flash point. Flash point class exercise. Okay, look up and record the flash point for the chemicals below and put in order of the most to least flammable. We're not going to do that. Well, it's already been done, but here's what they are. The flash point for diesel fuel, 136 degrees Fahrenheit. Gasoline, minus 45 degrees Fahrenheit. Benzene, 12 degrees Fahrenheit. Turpentine, 95 degrees Fahrenheit. So the order of flammability would be number 1, gasoline, number 2, benzene, 3, turpentine, and 4, diesel fuel. What are the ingredients for a fire? We all know the fire triangles, oxygen, heat, and fuel, and the tetrahedron of fire that goes in something called chain reaction. So what's a chain reaction? It's a reaction that just keeps on going. It doesn't. So that's what fire is until it's stopped. Explosive limit is the range that vapors will burn in the air. So we're going to look up and lower and upper explosive limits for these chemicals: kerosene, gasoline, and methylene chloride, which is furniture stripper. So the lower explosive limit for kerosene is 0.7 and the upper is 5. Gasoline, lower explosive limit 1.4%, and the upper explosive limit 7.6%. Methylene chloride, 13% is the lower explosive limit, and 23% is the upper exposure limit. So what do we know about this? What do we know about what do we call that area between the lower and the upper explosive limit? That's the flammability range. Between those two the concentrations, that's going to be flammable. Below it, it's too lean to burn, and above it, it's too rich to burn. So you can get too much of a good thing, I guess. What's the rule about vapor density for most chemicals encountered in construction work? Are they heavier than air or lighter than air? Now, most chemicals in construction work are heavier than air. What's that mean? When they're going to stick around, they're going to not float and waft up into the air. They're going to go down towards the ground, which makes it, depending on your situation, they might stick around longer. Section 5, measurement and exposure limits. Why do we monitor? Well, there are two types of monitoring: real-time and samples that are sent to a lab. So real-time instruments tell you right away, and samples sent to a lab, or also they can be done like in a drager. You put in the tubes, usually they're glass tubes. Sometimes you have to break off the end of them, and they will pull in air and give you a reading right there, as opposed to a meter that measures it as you look at it, which I think are the best to have. Real-time equipment can give immediate chemical exposure measurements. Combustible gases, toxic vapors and gases, oxygen. There's a guy holding a meter, and it looks like a mine. And there's a guy that has an air pump and a sampler on him that pulls that pump's pulling air through that sampler and monitoring it in the breathing zone. That's why I have it up there near his mouth to determine a specific employee's exposure. Recognizing these units will help you understand exposure results and OSHA limits: parts per million, parts per billion, milligrams per cubic meter, micrograms per cubic meter, percent, and fibers per cubic meter. Excuse me, for cubic centimeter. Parts per million, ppm, is a very small amount. About 4 drops of ink in a 55-gallon drum equal 1 part per million. Parts per billion is 1,000 times less than ppm. I don't like that expression, 1,000 times less than ppm. The right way is parts per million times 1,000 is parts per billion. So one tissue in a roll from New York City to London is 1 parts per billion. That roll will be pretty wet, though. Gram is a measure of weight. A paper clip is about a gram. Now, there's different sizes of paper clips, but your standard little paper clip. A milligram is 1,000th of a gram. So that would take 1,000 paper clips. Microgram is 1 millionth of a gram. They got a whole lot of paper clips then. Micrograms, rather. Milligram per cubic meter is a measure of the mass in the air. So you have milligrams per cubic meter, mg/m cubed, micrograms per cubic meter, micro g/m cubed, and a meter equal 100 centimeters, approximately 3 foot. Now you're talking about a length there. Just to give you an idea, a meter is just a little over a yard, but it's 100 centimeters. Cubic centimeters, a measure of volume. A thimble holds about 3 cubic centimeters of air. Do they even have thimbles anymore? I guess they do. OSHA has permissible exposure limits, PELs, but it's critical to remember most are from 1968 American Conference of Government Industrial Hygienists threshold limit values. Current threshold limit values are often lower. NIOSH recommended exposure limits are usually lower. Most chemicals have no exposure limits set. Most exposure limits are based on an average over 8 hours. They call that an 8-hour TWA, or time weighted average. And that would include like even your breaks and lunch, everything else. You leave that thing on for a full 8 hours. Some chemicals have ceilings that can't be exceeded. I mean, safely, they can't be exceeded. There's the ceiling in this particular instance here. So that's the end of section 3, 4, and 5. And hope you learned something about it. But read this section in the book. All the questions are going to come from the book. And don't just rely on this. This is kind of just trying to give you an overview of the high points of it. So that's all for today. I got to go feed the hummingbirds.